Hi, my name's Dave Ferreira, and this is the mechanical machine shop for mechanical engineering. Okay, so the first thing you need to do is go on Sakai and sign off that you read the safety protocol for the shop. All right. So at any point you come in here, I'm not going to let you go into an unsafe environment. So I'm going to make sure that you're dressed right and your hair's pulled back and you're wearing proper shoes and stuff like that before we let you in the shop. Okay. But basically what we do in here is we make machine components. And there's two basic styles that we make. A cylindrical base part, such as this, which will be made on the lathes, I'll show you in a minute, or a rectangular base part, which we do on the milling machines, which I'll show you in a few seconds here, okay? So in this case, we're going to buy bar stock, okay? And we're going to cut it on the drop-down saw, which I'm going to show you when we move down the line here. In this case, we're going to buy plate stock, which would come in a plate, and in this case, we would cut it over here on a horizontal bandsaw. Okay, so we're starting at the saws, and we're either using plate material on the horizontal, or on the vertical, or bar stock on the horizontal. So we're going to move down the line here. So this is the horizontal saw, which we use for bar stock, such as this, where we can slide in and cut the piece. In both cases, we're going to cut 1/8 of an inch bigger than what we need, so we can clean up a 1/16 on each side. So if this was 4 inches total, I would cut it to 4 1/8. That would allow me to take a 1/16 off that side and a 1/16 off that side to bring it in. Same thing if I was doing the plate material. If it was 5 by 4, I would cut it 5 1/8 by 4 1/8. That would allow me to face each side and bring it into the size and have enough material to do that. Okay, so we cut slightly bigger than we need. Okay. So we're going to come over to this machine here, and I'm going to show you the basic setups for machining a rectangular part like this. I'll get to the cylindrical in a minute. So whatever this thickness is, we'd like to design parts that have a known thickness, standard size. Like if this was 3/4, I could buy 3/4 inch by 4 inch by a length of it and cut these pieces out, okay? So the first thing we're going to do is come to our milling machine. This vise here has to be perfectly parallel with the x-axis, okay? So to do that, we put an indicator in here, we run it back and forth, and we loosen up one side and tap it until it reads 0, or the same reading all the way across. Then we know that the vise is parallel to the x-axis, okay? So in machining, there's 5 basic things. The first one is to have a rigid setup, meaning that when we hold a pot, it's not going to move when we go to cut it, all right? So that's the most important thing, a rigid setup. That's the first thing, okay? The next thing is RPM. What speeds do we run our cutters at? So these are all the cutters here. These are just some of the cutters. These are the ones I use the most. So there's end mills we use for cutting. There's 2 flute, 4 flute, multi-flute. So depending on what material and how hard they are, the materials that we're cutting, we use different styles of end mills. So the second thing is RPM. What RPM do we run at? So depending on how hard the material is, we use a formula. The cutting speed of the material, aluminum happens to be 200, times 4 divided by the diameter of the tool. So if we're using a 1/2 inch tool, so it's 200 times 4 is 800 divided by 0.5, which is a 1/2 inch, is 1600. So that's about the speed that we would run this cutter at. As the materials get hotter and hotter, we run slower and slower with the same tool. So just for instance, if we were cutting steel here, we'd be running about 800. So we'd run steel about half as slow as we do aluminum, okay? So that basic formula is the cutting speed of the material times 4 divided by the diameter of the tool, okay? The third thing is the feed rate. If this was an end mill and we were going to make a slice or a cut into this pot, I can set feed rates over here on this dial here. If I set it to 2, that's 2 inches a minute. So in milling, we feed in inches per minute, okay? So that's the third thing. The fourth thing is the depth of cut. So if I'm going to make a cut into this part here, I can come down and touch the top of the pot, work my way off it, and let's just say the cutter was right at the top of the pot. I could set 0 here, and if I had to take 250 deep cut, I'm not probably going to take that all in one shot, so I might take 50, and what I'm doing right now is raising the knee up. Okay, so I'm engaged 50 thousandths into the pot now. Now I can stand it up, engage my feet, and actually do the cutting. Okay, I'm not cutting now, but this isn't a cutter, this is an edge grinder. Okay? So we got rigid setup, RPM, how fast do we run, feed rate, depth of cut, and the last but not least, a sharp tool. So when I come in here and I grab a tool, I make sure it's sharp. Because if I'm cutting with a dull tool, I'm kind of almost like wasting my time here. Because it's not going to cut the material, it's going to actually maul the material. And what that does is create a lot of heat and gives you real bad finishes. Okay? So those are the 5 key things to machining. Okay? So if we have a print and we're going to make this pot, we have to set up a relationship from the center of our spindle to the back left corner of our part. So if we're dimensioning features on a print, let's dimension everything from the back left corner. So that once I call this 0, 0, now if this is 1.5 inches over and 1.5 inches down, I can go over there and read my readout and go right to that feature and put it in. Okay? So I'm going to show you how to pick up the edges to establish that relationship between the spindle and the piece. So you can see I got a magnet over here. I slide it up against the magnet, tighten it up so it'll stay in the same position every time. I'm going to bring my edge finder down into the pot and bring it over. You're going to see it slowly run truer and truer until it kicks out. I'm feeding it very slowly by hand until I get it to kick out. At the point it kicks out, I'm going to set my X to 0, and I'm going to make up for the radius of that. That's 200 thousandths, so I'm going to move 100 and re-zero it. So I just did the X-axis, now I'm going to do the Y-axis. It tripped out there, so I'm going to set 0 and make up for the radius, which is 100 thousandths. Now I'm going to go to 0, 0 and just double check myself. Make sure I went the right way. Okay, that looks right. So now if I'm going to put that feature in, I'm going to move 1.5 inches, I can read it directly off the readout. I don't have to do any adding and subtracting if we dimension everything in absolute from the back left corner. Okay. Now when we drill holes in this plate, we don't just put a drill in there and drill holes, we actually center drill. So I'm going to put a center drill in there and actually go in there and spot all these holes so I get perfect location to these holes. That, and then probably those 2 radiuses right there, and then each one of these slots I'm going to actually drill through first so that I'm not plunging straight down with my end mill because they don't like to plunge like a drill does. Okay? So to get parts, when we build assemblies, we need to center drill things so things go together properly. If we just come down and drill, the drill kind of wobbles around, finds its own home, and then we have misalignments. Okay? So that's the first setup that we do for basically rectangular parts. The second one I'm going to show you is when we do cylindrical pots. So if we did this pot on the lathe, we cut it 1/8 of an inch bigger, we'd chuck it on the lathe, I'm going to show you in a minute. We'd face it and turn it down, taking depth of cuts to get down to this diameter and to this length. Okay. We can also do work on the lathe in the center, so we'll put this hole through and we'll drill it and probably ream it out to its standard size. Hopefully it's a standard size. If it's not, we'd have to bore it out. Okay. Then we'd flip it over, face this. Now it's ready to go to secondary operations on the milling machine. because we can't put these bolt hole circles in on the lathe. We have to come over here. So I'm going to show you the setup to establish a relationship to this part here. So remember that the most important thing I said is to have a rigid setup. I'm going to use this V block because if I just clamped here to there, I'm clamping on an infinitely small area, and when I go to machine it, there's a good chance bad things are going to happen where the pot's going to move while I'm cutting it. So if I introduce a V block here, I can go from 2 points of contact to 3, and it makes it much more of a rigid setup. So instead of using the edge finder, you need to use the indicator. So we use the indicator quite a bit in the shop. So it's not only for measuring things, we use it quite a bit to pick up parts. And what I'm trying to do is establish a relationship between the center of the spindle and the center axis of this part. So I'm just going to move this to where I think it's kind of close. And I'm going to drop my knee down. And I'm going to put it in neutral so I can swing this around. And there's a little ball on the end of the stylus here. And I'm above the pot, but I want to make sure that I want to line it up where if I brought it down, it would just hit the pot, tangent to the ball. And I'm going to swing to the other side. And you can see I'm off by about 1/8 of an inch. So that means I'm going to move it 1/16 of an inch and reposition it. And then go back to the other side. And I'm going to move it I'm always moving it half the amount. So I reposition it, go back to the other side, looks pretty good. Then I'm going to bring my Y in. So now I'm going to actually engage the pot. I need to get that close because this only has 30 thousandths of travel. So if I don't get that close, it's just going to peak the indicator out, and I'm not going to get the reading I need. So as I bring the pot down, I'm going to push it in until it reads straight up and down and it's at 0. And I'm going to swing to the other side, and I can see it dropped off down to 15 or 14. So I'm going to move it half the amount like I've been doing all along, move it to 7 thousandths, set 0, and go to the other side, and I'm looking for 0. And I'm about 1 thousandth, so I'm just going to move it that half thousandth, re-zero it. Now when I come to this side, it should pretty much read 0. And now I'm going to bring it to the front and bring my Y in. At this point, when I swing it all the way around the pot, it reads 0. So that means that the center of my spindle is in perfect alignment with the center axis of the pot. At that point, I'm going to 0 my readout. So when we're dimensioning on the face of a cylindrical pot, we want to dimension everything from the center. So if I was going to put these 4 holes in and it's 750 over here, 3/4 of an inch, I set 0 there, I move to my 750, I put my center drill in there, I center drill the hole, then I replace it with a drill the hole, and then I put a tap in there and I tap the hole. Okay, and I do the progression of all 4 of them. So this is the second setup that we have to do for cylindrical base pots when we're machining on the face. Okay. A lot of times there's parts that aren't so symmetrical like this, like castings, where we have to build a fixture to hold the pot. We can positively locate that pot, and then we position these clamps onto the pot, clamp the pot down, and then the fixture goes in here, and now that we can actually hold the pot well enough to do some machining on it. Okay. So when we get odd-shaped parts like castings, generally there's fixtures involved that we use to hold the pot. Okay. All right, we're going to move over. Okay, so this is the lathe. This is where we churn cylindrically based parts. We can face here, we can churn down here. And we have 2 axes, basically the Z-axis and the X-axis. So after I face it off, I might want to set my Z-axis to 0. Then anytime I move the tool down this way, it's going to read out the amount that I need. Okay, so I'm going to read off the print and cut that amount. let's just say I brought the tool in and I just touched it on the floor. I could set this to 4 inches. So now as I bring the tool in, I can accurately cut. Now I'm going to take a measurement after I make a cut and make sure that I'm in line with that number, and if I'm not, I'm going to readjust that number. So that we can face over here, turn. We basically hold the pot in the chuck, and we spin it, and we feed the cutter either in the Z or in the X. So I can do work here on the diameter face, on the face, on the diameter, and internally in the center. And you can see we have a boring bar in there now. If this center hole was an oddball size, not a standard size that I didn't have a tool for, I could actually go in there and bore it with the tool like that. Okay. So over there, it was the diameter of the tool to determine the RPM. Over here, it's the diameter we're turning to. So if we're turning to 2 inches, it'll be 200 is the cutting speed for aluminum. Times 4 is 800 divided by 2 would be 400. So the diameter is the actual diameter we're turning here. That's the only difference in the RPM. The only other difference is the feed rate. Over there we feed in inches per minute. Over here we feed in thousandths per revolution. So if I set it to 4 thousandths feed rate, when I engage the feed, and it starts to feed across the pot, every time it spins once, it's feeding 4 thousandths. So we feed in thousandths per revolution over here. That's the only difference between milling and churning. Okay? Okay, we're going to stop. Okay, a lot of times when we're milling and churning, we're trying to establish tolerances of about plus or minus 3 thousandths. Well, we need to get much closer tolerances than that, or maybe into the 10 thousandths range. We need to leave the pots a little bit big. Generally we send them out to get heat treated, and then we come back and we grind them in. Okay? So in this machine I can grind to 10 thousandths tolerances. So if you look at these little pots here, these are made in a progressive die system where the material comes down through a progression of dies, and they do intricate work on stamping or piercing or notching or bending or reforming or drawing. To make those punches come down inside the dies with perfect alignment all the way around that have equal clearance, we need to grind those parts. So I just want you to know that when tolerances are extremely tight, we leave material on the pot and we go to grinding operations to do those dimensions. Okay? All right, we'll stop there. Okay, a vertical milling machine that we set up over there, this is an automated version of it. This is a CNC milling machine, okay? It basically does the same thing that does, but it's automated. When we load the program, we load all the tools, and we set all the heights for the tools, and we set the work shift offset for it. And once all that stuff is loaded in there, we can push the button and walk away, and it's basically, we'll go through the progression of milling slots, drilling holes, tapping holes, center drilling holes, whatever is needed on that pot. At some point I'm going to show you how to program these machines, and I'm actually going to show you how to set them up. So you're going to get a good understanding of what a production shop will do. When there's multiple pots, we do them on these machines. When there's very few or a single pot, we do them on those machines. Okay. Okay, so the basis of this class is for you to have an understanding of what machine, or what processes we use to develop parts. Okay, and these are some of the parts in manufacturing processes that we use to make parts. Okay, obviously you know what rapid prototyping is. What it does is it gives you a complex shaped part in your hand at very rapid speed. So you can evaluate what you got before you actually design a mold to actually injection mold that part. So you can work out all the bugs very quickly, and you will not have to modify the tool so much after it's made. So you're going to actually make sure the design is proper using this before you spend thousands of dollars to build a mold. Okay. This is sand casting, where we cast metal into intricate shapes cheaply and quickly. Okay, and I'm going to go over that in depth in a minute. So these are a couple of sand casted parts. Okay, and the casting has to be of higher quality. We investment cast it like this. So this is like a titanium shifting fork. Okay, so the materials are a lot better materials than we would use in sand casting, and their operations are extremely critical, and that's why we investment cast them. And basically, we'll make this pot out of wax, and then we'll dip it in a slurry of ceramic and build up the coating until it's hot enough to, and then we introduce a hole into it, and we pour the material in, and the wax melts away, and then we crack the ceramic and get the part out. So this is very labor intensive, but for aircraft parts and such, we investment cast those. Okay. When we need a cheap part, we die cast it. This is the half of a utility knife, and you can see the intricate shape that we can get through this. And how this works is there's little balls of like zinc-based alloy, and an auger spins and it brings the material into this little cauldron, and there's an induction heater, and it heats it up into a liquid form rapidly. And then a straight plunger comes in and pushes the molten material into a mold that's cool with water on both sides. It's allowed to set up, the mold opens up, it kicks it out, it closes, and repeats the cycle over and over again. So it's extremely fast, quick, efficient, and cheap. So that's die casting. Okay. And we have forging here, where the part has to be extremely strong. And the way this works is we heat this material up in an oven to like 1500 degrees, and put it in a giant press and come down and slam this pot until it slams down into its final shape. Okay, and then it's cut out, and then it'll go into a special fixture to get this side turned. Then another fixture here that'll turn the back side, and then it'll go to a grinding machine and they'll grind the lobe. Okay, so this could be in an engine that's actuating a cam to build oil pressure to bring the oil from the bottom of the tank up to the top of the motor. So this has a tremendous amount of stress on it. So in that case, we don't want to just pour it with cheap material. We want to use really good material, forge it, and then machine it. What this does is it aligns all the crystals in the same direction and makes the pot tremendously strong. Okay, so that's forged. Injection molding works pretty much the same way die casting is. Instead of using zinc-based pellets, they use plastic pellets. And you put them in a hopper, they go through the hopper. There's a chill plate to keep the heat from the screw and the barrel from going back up into the raw material. But this would be a mold. Let's just say this was a mold. The screw turns to homogenize the material, and then it pushes it forward. It goes forward to the back of the mold. The plunger pushes the amount in plus a little bit because there's shrinkage as this cools. And so some of the variables are how fast you push it in, the heat ranges on the heat bands. Each material has a heat range that it needs to be at. Then it's allowed to set up, the mold retracts, and this gets kicked out, the mold closes, and it repeats the process over and over again. Okay? So to build a mold like that costs thousands of dollars, so rapid prototyping beforehand will save a lot of rework to the mold. Okay? So these are just some of them. These are some of the most important ones. Okay? I'm going to show you how to cast a part. So let's say we were going to make these emblems here. These could be belt buckles, or these could be paperweights or whatever. Okay? So the first thing you need is a patent. And here's the patent that we use to make those. Okay? So let's follow the progression of the material. So anything that's above this surface is going to be an impression in the sand on one side. And everything that's sticking up above this is going to be the impression on the opposite side. So when we remove this, all these areas are going to be cavities. And we're going to fill in through the sprue. So let's follow the material if we're going to pour aluminum down here, or wax in this case. Okay? So this is the sprue. It's going to travel down the sprue to the runner. From the runners, it goes to the gates, and from the gates, it goes to the parts. Okay? Now all these edges here have draft angles on them, so they're not perfectly square edges. They're tapered in slightly, so when we pull this out of the sand, it releases properly. I know these look like straight edges, but they're not. Everything has a drift angle. So if I was designing this in Mastercam, and I clicked on that, I'd hit draft, the box would open up, and it would say, what draft angle do you want? And I'd put in 2 degrees, and then it's going to kick that over 2 degrees. Okay? So I want you to know the progression, the terminology, sprue, runner, gates, part, and draft angle. Okay? Where the 2 pieces come together, that's the potting line. So when we release this at the end, you can see the potting line right here. That's where the 2 halves come together, and there's generally some flash that comes out. Okay, so that's where the pieces of the mold meet when they're closed. Okay. So this is the cope and the drag. They're basically bookends that have grooves in the side. So when we tamper down the sand and clay mixture with water, it has a place to go in and hold up. So the first thing we would do is we have a sand and clay mixture. We add water to it till we get it to a consistency where when we squeeze it, it holds the shape really well and won't crumble, and it's not excessively wet. Okay. At that point, we have a screen here, and I'm going to take a little bit of talcum powder in a bag and just put a little coat of talcum powder on that. And then I'm going to shovel the sand and clay mixture in here and sift it through one last time. And I'm going to spread it out. I'm going to tamper the ends, the edges, and then the center. I'm going to do that about 3 times till I build a layer up that's higher than this ridge here. At that point, I'm going to scrape it off and just get it flush. Okay? So now, what we got is the emblems and the rail impregnated in the sand. And I'm going to flip it over. I'm going to put my sprue in. I'm going to flour it, and then I'm going to sift through it and tamper down about 3 times till I build a layer up above this. Then I'm going to scrape it. And then I'm going to dig my sprue out carefully. And then I'm going to release the patent. So in here I'm going to have the sprue hole with the gates. And in here I'm going to have the runner with the emblems. Then I'm going to reintroduce them. And then I'm going to pour the material down the sprue hole, which broke off what it would have been right here. So you can see that the potting line on this is right on this surface here. Then you allow it to set up, you pull it apart, and you basically have to go in there, and because the sand and the clay dry out because of the material so hot, you gotta bang it in the pot and break it up and get this out. And then this would go to like a bandsaw. They'd cut these off, and they'd probably grind those on a belt sander, and then they'd go off to wherever they're either gonna get machined or plated or what have you. Okay.